right, so here we're reviewing the events of the action potential. And so let's not do that. Okay. So let's start out with a graph here. So let's draw a graph on our y-axis. So here we've got the membrane potential. You know, this is in millivolts. And then we've got time on the x in milliseconds. Then we want to draw in our reference values. So the first reference value is that of rest. So on -70, this is our resting value here. And then let's draw in our threshold. Let's also think about our maximum membrane potential as well. So we've got -70, -55, and then +30, okay? So we know that the first, the first set of events is that from -70, where the cell is at rest, we have a series of graded potentials that could likely get us closer to threshold, okay? So that's gonna be the first segment of the events taking place here. And I'm gonna kind of be color coding these, so that's what the switching of colors is about. All right, then we have the rapid upstroke of the action potential, okay? And then we've got the opposite events where things kind of flip-flop here at +30, and then we've got the rapid downstroke. Remember, we go all the way down past -70 at this point, and then we overshoot, and then we get back to -70, okay? Let's actually make this a different color. All right, so we get all the way down here. And then let's make this a different color here. So we overshoot and then we get back to rest. So let's describe the events here and see what's happening during each of the phases. So let's start out with that first phase where we have graded potentials. So the first phase of the events here is where we've got graded potentials that could possibly bring us closer to our threshold value, okay? And so these are a sequence, and we'll talk about what this means here, but these are a sequence of IPSPs, which are inhibitory postsynaptic potentials. I'll talk about what that means a little bit later on, and as well as excitatory postsynaptic potentials. So basically inhibitory events or excitatory events, these are different types of graded potentials. And depending on what we get, this can get the membrane potential closer to -55. So this gets the membrane potential to that -55 millivolts, okay? The second set of events here are the depolarizing events, so the upstroke of the action potential. And so what happens here is we have sodium channels, our voltage-gated sodium channels, are essentially opening. So basically the movement that's responsible for the upstroke here is sodium moving into the cell. And that's because we have an increased permeability to sodium. Remember, this large P means the permeability of the membrane to the ion. And so an increase in sodium's permeability, which is really a result of activation gates being open. And inactivation gates also open. Okay, and now we also want to be thinking about what's happening with potassium here as well, as far as the permeability. So during this phase, there's a decreased permeability for potassium, and that's because our voltage-gated potassium channels are closed. Alrighty, and so essentially what happens here is that the membrane potential becomes positive in an attempt to approach the equilibrium potential of sodium. So that's the essence of depolarization. Let's look at repolarization. So during repolarization, we see an opposite movement of ions. This is the movement of potassium out of the cell. Okay. And that is because we now have a decreased membrane permeability to sodium, which is really a result of the channels being inactivated. Remember, when we say that the channels are inactivated, we're really saying that the inactivation gates are closed. Okay, although the activation gates are open. Okay, and so the channel is inactivated here, right? And that's what's responsible for that, that shutting, that twisting or turning or flipping of the events at positive 30. And now we see that the membrane permeability to potassium increases, and that's because the voltage-gated potassium channels, open up. So voltage-gated potassium channels open here. And so what's really happening is that the membrane potential is becoming more negative. Alrighty. And then the final stage or phase or sequence of events here is that we've got hyperpolarization. This is where the membrane undershoots, or we can think about it as being overshoot in terms of the direction of movement, the resting membrane potential. All right, so the fourth phase here, hyperpolarization. Here we have an increased permeability to potassium because our voltage-gated potassium channels are closing, right? Really important here, they're still actively closing. And so the membrane potential doesn't stay at -70, right? We're still trying to approach potassium's equilibrium potential. And what's really important here is that it overshoots rest, so the membrane potential overshoots rest. And then the sodium potassium pumps are what kick in to bring us back to our resting value. So the sodium potassium pumps are really important at this point. These help to restore the -70, which is the resting membrane potential. Okay. So the essence of the hyperpolarization phase is that potassium channels are still actively closing. They're not all closed. And as long as they're not all closed, the membrane potential will still be trying to approach the equilibrium potential for potassium, which we know is -94. Until all of those, until the very last potassium channel closes, and the sodium potassium pump starts kicking in, then we'll start seeing that correction of the membrane potential, and it gets back to negative.